In this chapter, we'll be discussing concepts related to probability. Probability is a separate math course in and of itself. So we'll be just looking at the very basic concepts pertaining to probability. The first concept we're going to discuss is that called the counting principle. The counting principle states that if an event can occur in m different ways and another independent event can occur in n different ways, then they can occur together in m times n number of ways. So here's our first problem. We have 4 candidates for president and we have 3 candidates for Senate. Assuming that our choice of senator is not related or dependent upon our choice of president, then how many ways can the 2 offices be filled? Well, according to the counting principle, since the office of president can be filled in 4 different ways, and the office of Senate can be filled in 3 different ways, together they can be filled in 12 different ways. M times n, which is 4 times 3, which is 12. Now, we can illustrate that using what I call a tree diagram. So we have 4 choices for president, and we have 3 choices for Senate. So I can elect President 1 and Senator 1, or President 1 and Senator 2, or President 1 and Senator 3, or President 1 and Senator 1, or President 2 and Senator 2, or President 2 and Senator 3. Or I could elect President 3, Senator 1, President 3, Senator 2, or President 3, Senator 3. Or I could elect President 4, Senator 1, President 4 and Senator 2, or President 4 and Senator 3. Now, I've illustrated by a tree diagram all the possibilities of filling those 2 offices. So if you count them, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which agrees with the counting principle. Now, the counting principle can be extended beyond just 2 independent events. It can be extended to any number of independent events. So in the next problem, we're going to utilize the counting principle as well. However, here we're trying to determine how many different license plates of 6 characters that can be formed if the first 2 characters must be letters and the last 4 characters must be numbers. And here we're allowed to repeat both the letters and numbers. So, for the first character, I have 26 possibilities, 26 letters in the alphabet. Now, my choice for the second letter is not dependent upon the choice for the first letter. So the 2 events are independent. So I still have 26 possibilities for the second character. The third character must be a number. So we have the digits 0 through 9, which actually gives us 10 possibilities for the third character. Now, the digit that I choose for the third character doesn't affect the choice of the digit that I choose for the fourth character. So I still have 10 ways. If I'm filling the fourth character with a number, I still have 10 ways in which to fill the fifth character with a number, and I still have 10 ways in which I can fill the last character or the sixth character with a number. So how many different license plates can be formed using 6 characters, of which the first 2 must be letters and the last 4 numbers? Well, that is simply 26 times 26 times 10 times 10 times 10 times 10, because all of the events are independent. So I simply multiply the number of ways that I can fill each of the 6 spaces together. which gives me 6,760,000. Now, that may sound like a lot of license plates, but in reality, for a state the size of California, which is one of the more populated states in the U.S., that may not be enough individual license tags. Remember, these tags are good for several years, and there may be some families that have more than one vehicle. So how could we increase the number of license tags for the registered vehicles if we're still only using 6 characters? One way is we could change one or more of the digits to letters, which would increase the number of tags that we can make. Another example of the counting principle, and remember what the counting principle states: if an event it can occur in m number of ways and another independent event can occur in n number of ways, then they can occur together in m times n. But we've just seen from the last example that that can be extended to any number of independent events. So here we have another situation where we're trying to determine how many 3-digit security codes can be formed if the first digit cannot begin with 0. Well, there are digits 0 through 9, which gives us 10 digits, but if we cannot fill the first code using a 0, then that means we can use the numbers 1 through 9, so there are 9 possibilities there. Now, there's nothing special about the last 2 digits. We can use any of the 10 digits for the remaining 2 characters. So I have 10 choices for the second character and 10 choices for the third character. So how many 3-digit codes can be formed using the stipulation that the first character cannot be a 0? 9 times 10 times 10, which is 900. Now, in the next several sections, we're actually going to discuss concepts related to probability. The first probability we're going to discuss is that called classical probability. And in classical probability, you do not actually have to perform an experiment to determine the probability of a certain outcome. Before I deal too much with the concept of probability, there are some associated terms. An outcome is the single result or trial of a probability experiment. An outcome is the single trial of a probability experiment. A sample space is a set of all possible outcomes of a probability experiment. So if our probability experiment is tossing a coin, then we have the sample space, which includes heads and tails. If our probability experiment is that of rolling a die, then our sample space would be the numbers 1 through 6 inclusive. So the next thing we're going to do is define classical probability. And what we're defining is the probability of the successful occurrence of an event. We're defining the probability of the successful occurrence of an event. So, if we're trying to determine the probability of the successful occurrence of an event, if S represents the number of chances for success, or another way of putting that is the number of ways that what you want to happen can happen, then the probability of success is equal to S over n, where n is the total number of outcomes. So the probability of the success of an event, definition, classical probability, is equal to the number of ways what you want to happen can happen, or the number of chances for success, S, divided by the total number of outcomes. So here we have a spinner to the left, and we want to know what is the probability of obtaining a number which is a multiple of 3. So what we need to do is ask ourselves, how many chances for success do I have? Here, success is obtaining any number which is a multiple of 3 on this spinner. So 3 is a multiple of 3. 6 is a multiple of 3. So if the spinner lands on 3 or 6, what I want to happen has happened. So I have 2 chances for success. However, there are 6 possible outcomes, because the spinner can land on any one of these 6 digits. So the total number of outcomes is 26, which is equal to 1/3. And of course, I could write that as a decimal. I take the fraction and write it as a decimal by simply dividing 1 by 3, and that would give me approximately 0.33, rounded off to the nearest hundredth. Or I could also express the probability as a percent, which would be approximately equal to 33%. Actually, it's 33 1/3%. Now, note that probability is always a number between 0 and 1. It's always going to be a fraction or a decimal number between 0 and 1. A probability of 1 represents an event that is sure to occur. So if we look at the spinner above and we ask ourselves, on a single spin, what's the probability of obtaining an odd or an even number? So if I spin and I obtain an odd number, 1, 3, or 5, then what I want to happen has happened. Or if I obtained an even number, 2, 4, or 6, then what I want to happen has happened. So I have 6 chances for success. If I obtain one of the odd numbers, then what I want to happen has happened. If I obtain one of the even numbers, then what I want to happen has happened. So I have 6 chances for success. Remember our definition. The probability of success is equal to the number of ways what you want to happen can happen divided by the total number of outcomes. So I have 6 chances for success divided by total number of outcomes, which is 6, which is equal to 1. If I spin, then I'm going to either obtain an odd or even number. So the probability for success there is 1. It is sure to happen. A probability of 1 represents an event that is sure to occur, whereas a probability of 0 represents an event that will never occur. Again, we're using the spinner as an example. So what's the probability of attaining a 7 on the single spin if this is our spinner? Well, there is not a 7 on this particular spinner. So the number of ways what I want to happen can happen is simply 0 over the total number of outcomes, which is 6, and 0 over 6 is 0. Here it's impossible to obtain a 7 if we only have the digits 1 through 6 on the spinner. again, considering the spinner with the digits 1 through 6 on it, we want to talk about how probability of success and probability of failure are related. The probability of success is equal to 1 minus the probability of failure, and vice versa. The probability of failure is equal to 1 minus the probability of success. So earlier we talked about the probability of getting a multiple of 3. The probability of obtaining a multiple of 3 is one third, or 2/6. So the probability of failure, or the probability of not obtaining a multiple of 3, would be equal to 1 minus the probability of success. So that would be 1 minus 1/3, which is 2/3. The probability of failure is equal to 1 minus the probability of success. So if the probability of success is obtaining a multiple of 3, the probability of failure would be failure to obtain a multiple of 3, which would be 1 minus the probability of success, which is 1 minus 1/3, which is 2/3, which makes sense since there are 4 numbers on that spinner which are not multiples of 3. They're 1, 2, 4, and 5. So there are 4 digits that are not multiples of 3. So the probability of not attaining a multiple of 3 would be 4 out of 6, which is equal to 2/3, which is what we obtained here. We are still discussing classical probability. And again, by definition, the probability of success is equal to the number of ways what we want to happen can happen, or the number of chances of success divided by the total number of outcomes. So here I have a pair of dice, and I want to know what is the probability of attaining a sum of 9 on a single toss of a pair of dice. So here I want the probability of obtaining a sum of 9. So the first thing I need to do is determine the number of chances for success, and I'm going to divide that by the total number of outcomes. So the best way to do this is to look at this systematically and list your sample space. So how can I get a sum of 9 on a single toss of a pair of dice? So I could get 3 on the first die and 6 on the second die, 4 on the first die and 5 on the second. You see how I'm listing these systematically in order. I could get 5 on the first die and 4 on the second, or I could get 6 on the first die and 3 on the second. So here are my chances for success. If I obtain any one of these combinations on that single toss, then what I want to happen has happened. So I have 4 chances for success. But be careful here. Here's where students make a mistake. A lot of times they tell me that the total number of outcomes would be 12 because there's 6 numbers on the first die and 6 numbers on the second die. Well, no, you have to apply the counting principle. If one event can occur in m number of ways, so that I have 6 choices for the first die, and another event can occur in n number of ways, I have 6 choices for the second die, then they can occur together in m times n number of ways. So when I toss a pair of dice, there are 36 possible outcomes. 4 of those result in a sum of 9, which is equal to 1/4 or 0.25. Remember that probability is always a number between 0 and 1. we're still discussing classical probability. And in classical probability, you do not actually have to perform an experiment in order to determine the theoretical, which is also referred to by probability. So in this particular situation, we're going to be working with a standard deck of cards. A standard deck of cards contains 52 cards, and there are 4 suits, and the suits are clubs and spades, which are black, and hearts and diamonds, which are red. In each suit, you have the numbers 2 through 10. You have an ace, and you have a jack, queen, and king. And the jack, queen, and king are called face cards because they have a face on them. So there's a lot of things that we can do in reference to probability using a standard deck of cards. So if a card is drawn at random from a standard deck, we want to know what is the probability of obtaining an ace. So success here is obtaining an ace. Again, we're using our standard definition of classical probability, and we have to ask ourselves, how many ways can what we want to happen happen? Well, if we get the ace of clubs, we are successful. If we obtain the ace of spades, we are successful. If we get ace of hearts or ace of diamonds, then what we want to happen has happened. So I have 4 chances for success out of total number of outcomes. There are 52 cards. Now remember, there are 4 suits, 52 cards, so 4 divided by 52 is 13. So there are 13 cards in each suit. The next question is, what is the probability of obtaining a spade? So if I get any of the cards with a spade on it, then what I want to happen has happened. I have the ace of spades, the 2 of spades, the 3 of spades, the 4 of spades, etc. So if I obtain any one of the cards with a spade on it, then what I want to happen has happened. And again, there are 13 cards in each suit, so there are 13 spades. And 13 out of a total of 52 cards is equal to 1/4, which is 0.25. And of course I didn't write this as a decimal. 4 over 52 written as a decimal. That's 0.0769, which is approximately equal to 0.08. And generally I'll tell you what place value I want you to round off to. What is the probability of attaining a red card? So success here is defined as obtaining a red card. So all of these cards, hearts and diamonds, are red. So if I obtain any one of these cards, then what I want to happen has happened. So there are 13 hearts which are red, and there are 13 diamonds which are red. So my chances for success, which is obtaining a red card, is 26 out of 52, which is 1/2, or 0.5. And that makes sense because half the cards are red and half the cards are black. Half of 52 is 26. We're still working with a standard deck of cards and using our definition of classical probability. So here success is defined as obtaining a face card. Now remember, the face cards are the ones that actually have a face on them, excluding jokers, because jokers are not included in the standard deck. So my face cards are Jack, Queen, and King. So I have 3 face cards in each suit, and there are 4 suits, so that's 4 times 3, which is 12 face cards. So if I get the Jack of Clubs, I have a face card. If I obtain the Queen of Hearts, I have a face card. If I select the King of Spades, then I have a face card, etc. So I have 12 chances for success out of a total number of cards of 52. And of course, if I divide 12 by 52, then that gives me approximately 0.2307, or round it off to the nearest hundredth, that would be 0.23. Again, remember, probability is always a fraction or a decimal between 0 and 1. The next question is a little bit more difficult, but nonetheless can still be answered. I want to know, if I select one card at random, what's the probability of obtaining an even number? So looking at my cards here, look at my even numbers. 2, 4, 6, 8, and 10. So I have 5 even numbers in each suit, and I have 4 suits. So if I get any one of these even numbers, 2 of clubs, 4 of hearts, 6 of spades, 8 of diamonds, etc., then what I want to happen has happened. So that's 5 even numbers in each suit. There's 4 suits. So my chances for success are 5 times 4, which is 20, out of a total number of outcomes of 52. And if I convert that to a decimal, that's approximately equal to 3800ths. All the examples that we've performed so far have been classical or theoretical probability. The difference between theoretical or classical probability and empirical probability, which is what we're going to look at next, is that for the classical or theoretical probability, the experiment does not need to be performed in order to determine the probability, whereas empirical probability relies on the actual results in reference to determining the probability. For example, here what we have is the age of employees at a certain firm, and what we want to determine is the probability that if an individual is selected, that their age will fall in a certain category. So the first thing we need to do is define empirical probability. So the definition of empirical probability will be very similar to that of our classical probability. The probability that an event will fall in a certain class is given by the probability of the event, which in this case is the same as the probability of success, is equal to the frequency of that class, which is F, divided by the total number of outcomes. And of course, the total number of outcomes would be the sum of all the frequencies for all the classes. So here, the sum of the frequencies, or the total number of outcomes, would be equivalent to or equal to 1,000. Now, that will be very dependent upon your data. So again, the definition of empirical probability is the frequency of that class divided by the total number of outcomes. And of course, the probability of the event here is also very similar to the probability of success. So the first example here is we want to know what is the probability that an employee, if selected at random, their age would fall between 25 and 34. So the definition of empirical probability, the probability of that event occurring, would be equal to the frequency of that class, which is 25 to 34, and the frequency of that class is 366, because I have 366 employees in that firm that ages range from 25 to 34, over N, which is the total number of outcomes, or the sum of all the frequency, which is 1,000. So 366 divided by 1,000 is 0.366. And again, probability is always a number between 0 and 1. We want to know the probability of the next event occurring, and that is the probability that if I select an employee at random, their age will be between 45 and 64. So I have 100 employees that fall in the 45 to 54 category, and I have 125 employees that fall in the 55 to 64 category. So if I want to know the probability that the employee's age is between 45 and 64, then I will combine these two categories, which will give me the sum of the number of employees whose ages fall between 45 and 64. So if I choose an employee in this category, then what I want to happen has happened. If I choose an employee and they fall in this category, then what I want to happen has happened. So I have 180 plus 125, which gives me 305 chances for success out of a total number of employees of 1,000, which would be equal to 0.305. So again, the difference between classical and empirical probability is, in the classical probability, you don't actually have to perform the experiment in order to determine the probability, whereas empirical probability is actually based on the data or results from the experiment itself. So in all the previous examples, we have been trying to determine the probability of the occurrence of a single event. But now we're going to look at determine the probability of the occurrence of two or more events. So the first set of events that we're going to discuss is independent events. Now, we mentioned this in reference to the counting principle, but I really didn't define what an independent event is. So two events are independent if the occurrence of one, or the non-occurrence of one for that matter, does not affect the probability of the occurrence of another. So again, two events are independent if the occurrence of one does not affect the probability of the occurrence of another. Example, if I toss a coin 3 times and heads appears each time, then what is the probability of getting a head on the 4th toss? Well, just because I obtained heads on the first 3 tosses, that does not affect the probability that I'll get heads on the 4th toss. The probability that I get heads on the 4th toss is still 1/2. So what I get on the 4th toss, or the probability of what I get on the 4th toss, is not affected by what I got on the first 3 tosses. So the events are independent. Now, when we're trying to determine the probability that two independent events both occur, we're trying to determine the probability that A and B occurs. And the connective here is very important. The connective here is and. And in general, not always, but in general, anytime you see the connective and, then what's going to happen is you're going to multiply their individual probabilities to determine the probability that both events occur. So if A and B are independent events, the probability that both A and B occur, denoted using this symbol, is equal to the probability that A occurs times the probability that B occurs. In other words, if the two events are independent and you want to determine the probability that both occur, then you simply multiply their individual probabilities. For example, a coin is tossed twice. What is the probability that you get heads on the first toss and heads on the second toss? Now again, what I get on the first toss doesn't affect the probability of what is obtained on the second toss. So what I do is determine each of their probabilities separately. The probability that I get heads on the first toss is 1/2. The probability I get heads on the second toss is 1/2. So the probability that I obtain heads on both tosses is equal to the product of their individual probabilities, which is 1/2 times 1/2, which is 1/4, or approximately 0.25. So again, if the events are independent and I'm trying to determine probability that they both occur, then I multiply their separate probabilities. And we can demonstrate this by simply creating the sample spaces. If I toss two coins, here are all the possible outcomes. I could get heads on the first toss, heads on the second toss. I could get heads on the first toss and tails on the second toss. Or I could get tails on the first toss and heads on the second toss. Or I could get tails and tails. So there are 4 possible outcomes, and only one of those results in obtaining both heads. So that's 1/4, which is the same thing we got here by multiplying their separate probabilities. We are still looking at events which are independent. So I'm drawing 2 cards at random, and I'm replacing the first card before I draw the second card. Now, with replacement is very important, and we'll discuss why when we look at dependent events. So I want to know what is the probability of obtaining an ace followed by a face card in that order. So the two events are independent. Notice your connective here is and. In general, when you see the connective and, you're going to multiply their separate probabilities. So I want to know the probability of getting an ace on the first draw. And if I put that card back, what is the probability of getting a face card on the second draw? Now remember our definition of probability. How many ways can what I want to happen happen? There are 4 aces in the deck, and there are a total of 52 cards. So the probability of getting an ace on the first draw is 4 out of 52. Now remember the face cards are Jack, Queen, and King. So I have a Jack, Queen, and King in each suit, and there are 4 suits. So that's 4 times 3, which makes them 12 face cards. And if I put the first card back before I draw the second card, then I still have 52 cards to choose from, or 52 cards in the deck. So these 2 events here are independent. So if I want to know the probability that they both occur in that particular order, I multiply their separate probabilities. So 4 times 12 is 48, and 52 times 52 is 2,704. And if I divide 48 by 2,704, that's approximately equal to 0.018. Now, the next example also represents events which are independent. In a recent Gallup poll, 46% of the Americans indicated that they approve of President Trump's handling of the economy. So if I choose 3 people at random, what is the probability that all 3 say they approve of the way that President Trump is handling the economy? Now, regardless of what the first two will indicate, the probability that the third person indicates that they approve of the way President Trump is handling the economy is still 0.46, which is 46% written as a decimal. The same goes for the second person asked. Doesn't matter what the response the first person gave. If we choose the second person at random, then the probability that they approve of President Trump's handling of the economy is still going to be 0.46. So all three events are independent. So basically what I want to know is what is the probability the first one approves, second one approves, and the third one approves. So what I do is I multiply their independent probabilities, which will be 0.46 times 0.46 times 0.46, which is approximately equal to 0.097. So there's about a 10% chance that all three would indicate that they approve of the way President Trump is handling the economy. So two events are independent if the occurrence of one does not affect the probability of the occurrence of another. In the last section, we discussed independent events, and two events are independent if the occurrence of one does not affect the probability of the occurrence of another. In this section, we're going to talk about dependent events, and the major difference is when we discuss dependent events, the occurrence of one does affect the probability of the occurrence of another. When two events are dependent, to find the probability that both occur, just as we did for the independent events, we're going to multiply their separate probabilities. So again, the probability that two dependent events both occur is equal to the probability that the first one occurs times the probability that the second one occurs, given that the first one has already occurred. So here's the way we express that. This means the probability of A times the probability that event B occurs, given that event A has already occurred. This is not a division symbol here. Again, this is read the probability of B given A has already occurred. So let's look at some situations here, and let's see if we can determine what distinguishes two dependent events from that of independent. So here we have a jar which contains 5 red, 3 blue, and 7 green marbles. And what we're going to do is draw 3 marbles at random without replacement. Now this is very important. Without replacement means that we're not going to put the first marble back before we draw the second one. And likewise, we're not going to replace the second marble before we draw the third one. Now, the probability that two or more dependent events all occur is equal to the product of their separate probabilities. So we're still multiplying the probabilities. And again, notice that the connective here is still and in general, when we are or see the connective and, then we are going to multiply or find the product of their separate probabilities. So what's the probability of getting a red marble on the first draw, a blue marble on the second draw, and a red marble on the third draw? So the probability that we get a red marble on the first draw, well, there are 5 red marbles in the jar, so that's 5 out of a total of 15. Now, notice that what we obtain on the first draw does affect the probability of what we obtain on the second draw. The probability of getting a blue marble on the second draw is 3, because we still have 3 blue marbles left in the jar if the first one was a red one. However, what we get on the first draw does affect the probability of what we get on the second draw. In this case, if nothing else, that's because we have 1 less marble to choose from. If we did not replace the first marble before we drew the second marble, then there's 1 less marble in the jar to choose from, so that reduces our total number of outcomes. So the probability of getting a blue marble on the second draw is 3 out of 14. The probability of getting a red marble on the third draw is 4. Why 4? Because we're assuming that we drew a red marble on the first draw. Remember, dependent events is equal to the product of their probabilities. But we're assuming that the probability event V occurs after A has already occurred. So we're assuming that we already have drawn a red marble on the first draw. So the probability of getting a red marble on the third draw is going to be 4, because we have 1 less marble to choose from, 1 less red marble to choose from, and 2 less marbles to choose from than we started with. So that is 13. Because if we don't replace the first 2 marbles before we draw the third one, then we only have 13 to choose from on our third draw. So the probability of getting a red marble followed by a blue one followed by another red one in that order would be 5/15 times 3/14 times 4/13, which is equal to 60 over 2,730, which is approximately equal to 0.022. Again, the main distinction here between the independent and dependent events is that with the independent events, replacement has occurred, whereas with the dependent events, replacement has not occurred. So here we want to determine the probability of drawing a king on the first draw and a queen on the second draw if we draw 2 cards at random without replacement, meaning we're not going to replace the first card before we draw the second card. So again, that makes the 2 events dependent, because it does affect the probability of what I get on the second draw, because I have 1 less card to choose from. So the probability that I get a king on the first draw is 4 out of 52, because remember, I have a king in each suit. So I want a king on the first draw, and again, here's that connective and in general, when you see the connective and, you're going to multiply the probabilities. I want a king on the first draw, and assuming that I get a king on the first draw, what's the probability that I get a queen on the second draw? Well, if the first card is a king, then I still have 4 queens to choose from, but I only have a total now of 51 cards because I didn't put the first card back before I drew the second one. So I multiply their separate probabilities, which gives me 16 over 2,652, which is approximately equal to 0.006. Now this is called conditional probability because when I determine the probability of getting a queen, I'm assuming that I've already attained the king on the first draw. So the probability of getting a queen is conditional upon the fact that I've already drawn a king on the first draw. So far we have discussed independent and dependent events, and in general when you see the connective and, then in general we're going to multiply their separate probabilities. Now we're going to discuss two events we're called mutually exclusive. And two events are mutually exclusive if the occurrence of one excludes, hence the name exclusive, the occurrence of another. In other words, they cannot both occur at the same time. They have no outcomes in common. And in general, if you're trying to determine the probability some one of a set of mutually exclusive events will occur, then that will be equal to the sum, not the product, but the sum of their separate probabilities. And again, notice that in this case, you see the connective or. So these connectives are very important. In general, if you see the connective or, then the events are mutually exclusive, and you're going to take the sum of their separate probabilities. For example, find the probability of obtaining a sum of 6 or a sum of 9. Now, these two events, I could say, are mutually exclusive, because if I obtain a sum of 6, then that's going to prevent me from obtaining a sum of 9 and vice versa. So they both can occur at the same time. So if I want to know the probability of obtaining a sum of 6 or 9, then what I need to do is to find the sum of their individual probabilities. So I need to determine the number of ways that I can obtain a 6. So again, I'm going to write those systematically. 1 and a 5, 2 and a 4, 3 and a 3, a 4 and a 2, and a 5 and a 1. So I have 5 chances for success out of 36. Remember, when I toss a pair of dice, I have 6 possibilities on one and 6 possibilities on the other. So according to the counting principle, I have 6 times 6, which is 36 ways that they can occur together. The sum of 9, I think that we've already discussed that earlier. To obtain the sum of 9, I can have 3 on the first die, 6 on the second, 4 and 5, 5 and 4, and 6 and 3. So there are 4 ways that I can obtain a sum of 9. So the probability of attaining a sum of 6 or 9 would be the sum of the separate probabilities, which is 1/4, which is 0.25. Again, here I'm trying to find the probability that if a card is drawn at random, that I obtain either a face card or a red card. Now again, you see the connective or, so that generally means that I'm going to take the sum of the separate probabilities. But these events are not truly mutually exclusive, and I'll explain to you why. Well, the probability of getting a face card is 12 out of 52. Remember, the face cards are Jack, Queen, and King, and there are 3 of those, and there are 4 suits, so that's a total of 12 face cards out of 52. Remember, the red cards are both diamonds and hearts, and there are 13 cards in each suit, so there are a total of 26 red cards. So the probability of getting a face card or a red card would be 12 over 52 plus 26 over 52 if the events were truly mutually exclusive. That means the occurrence of one would prevent the occurrence of the other. And that's not the case here, because if I obtain a face card, that doesn't necessarily exclude me from getting a red card. Why? Because I have face cards that are also red. So one does not necessarily exclude the other. So if the events are not mutually exclusive, then I'm going to take the sum of their probabilities, but I've got to subtract the outcomes that they have in common. That is, where the two sets overlap. Here, if I simply add these two numbers together, I'm counting some of the cards twice, because I have face cards and I have red cards, but I also have red face cards. So think about this. I have a jack, queen, and king of diamonds, which are red, and I have a jack, queen, and king of hearts, which are red. So I've counted those 6 cards here in the face cards, and I've also counted those 6 cards within the red cards. So I've counted those 6 cards twice, so I have to turn around and subtract 6 over 52 from that sum, because I've counted 6 of the red face cards twice. I've counted them here and here. So I need to subtract from the sum the outcomes that they have in common. So that would be equal to 26 plus 12 minus 6 is 32 over 52, which is approximately equal to 0.615. So if the events are not truly mutually exclusive, after you find the sum of their separate probabilities, you have to subtract the outcomes that they have in common. In the last couple of sections, we're going to use what we call factorial notation, and that's usually denoted with a sign that looks like this, and this is read n factorial, and n factorial is the product of the whole numbers from 1 to n. So 4 factorial would be the product of the whole numbers from 1 to 4. So 4 factorial would be equal to 1 times 2 times 3 times 4, which is 1 times 2, which is 2. 2 times 3 is 6. 6 times 4 is 24. And of course, I could write that in reverse as well, because multiplication is commutative. It doesn't matter what order I multiply a series of numbers in, I get the same product. So this is the same as 4 times 3 times 2 times 1. And usually I write it this way. It's still equivalent to the product of the whole numbers from 1 to n. So likewise, 6 factorial would be equal to the product of the whole numbers from 1 to 5, but I generally write it in the reverse order. 6 times 5 times 4 times 3 times 2 times 1. 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. 360 times 2 is 720. And of course, 1 times anything is anything. So that's 720. And we have 2 special definitions that relate to factorials. 1 factorial is equal to 1 by definition, and 0 factorial is equal to 1 as well. Now here we have 10 factorial divided by 7 factorial. And this is the reason I write the factorializations backwards. Now we can only cancel equivalent factorials. I'll show you what I mean by that with this example. 10 factorial is equal to 10 times 9 times 8 times 7 factorial. I can stop at 7 factorial. I don't need to expand this all the way to 1, because 10 times 9 times 8 times 7 factorial, well, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. But the purpose of stopping the factorialization of the largest number here is now I can cancel the 7 factorials. Now you can only cancel equivalent factorials. So I can cancel the 7 factorials, which gives me 10 times 9 times 8, which is equal to 720. Now again, I must caution you here, you can only cancel equivalent factorials. So 6 factorial divided by 3 factorial is not 2 factorial. You cannot divide these as you would whole numbers. What you have to do is begin the factorialization of the largest number until you have something which you can cancel. You can only cancel equivalent factorials. Both of these are equivalent, 3 factorial, 3 factorial. So 6 factorial divided by 3 factorial would be equal to 6 times 5 times 4, which would be equal to 30 times 4, which is 120. Likewise, if I had a combination, 3 factorial times 6 factorial divided by 4 factorial. Now, again, I could compute 3 factorial and 6 factorial, multiply them together, and I can compute 4 factorial and then divide, but it's simply easier to begin with the largest factorial and write that factorialization backwards until you can find something which it will cancel with. Now again, you can only cancel equivalent factorials. That is 4 factorial with 4 factorial, or 3 factorial with 3 factorial, or 7 factorial with 7 factorial. So that gives me 3 factorial times 6 times 5. Now here I have no choice but to utilize or expand the factorialization of 3. So that's 3 times 2 times 1 times 6 times 5. So again, you can't multiply factorials and ordinary whole numbers. You have to either express them all as whole numbers. So 3 times 2 is 6, 6 times 1 is still 6, 6 times 6 is 36, and 36 times 5 is 180. So this is factorialization. The next concept we're going to talk about is a permutation. And a permutation is the arrangement of all or part of a number of objects in a definite order. So each time we change the order, we have a different permutation. Here, permutations are arrangements of all or part of a number of objects in a definite order. So list the permutation of the letters A, B, C taken 2 at a time. So I'm going to choose 2 of the letters, and I'm going to find how many different arrangements of those 3 letters that I can derive taken 2 at a time. So I have A, B, but if I change the order, I have a different permutation, B, A. So I can have B, C, and C, B, and I can also have A, C, and C, A. So there are 6 permutations of the letters A, B, C taken 2 at a time. Now we have a formula which we can use to compute the number of permutations of n objects taken r at a time. And it's given by the formula n factorial over n minus r factorial. So in this particular case, n is 3, so I have 3 letters, and r is 2. I'm taking them 2 at a time. So according to our definition, that's n factorial over n minus r factorial. So n is 3, so that's 3 factorial, over n minus r, which is 3 minus 2 factorial, which is equal to 3 factorial over 3 minus 2, which is 1 factorial. And of course, 1 factorial by definition is simply 1, and 3 factorial would be 3 times 2 times 1, which is equal to 6, which is the same thing that we got by listing all the possibilities using a sample space. However, sometimes there are such a large number of permutations that it's not feasible to list them all like I have done in the first example. And here's another example indicating that. Find the number of permutations of 6 objects taken 4 at a time. So n is 6 and r is 4. So that's n factorial over n minus r factorial, which is equal to 6 factorial over n, which is 6, minus r, which is 4 factorial, which is equal to 6 factorial over 2 factorial. So that's equal to 6 times 5 times 4 times 3 times 2 factorial. Remember, I stopped here because now I can cancel equivalent factorials. So my answer is 6 times 5 times 4 times 3. And 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. So here it would be very difficult to list all the possible permutations of 6 objects taken 4 at a time because there would be 360 of them. So I'm going to pause here and I want you to find the number of permutations of 10 objects taken 8 at a time. So I'm going to give you about 30 seconds to do that. So what I want to know is the number of permutations of 10 objects taken 8 at a time. So the formula that we have is the number of permutations, P stands for permutation, of n different objects taken r at a time would be equal to 10 factorial over n minus r, which would be 10 minus 8 factorial, which is equal to 10 factorial over 2 factorial, which would be equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial, all over 2 factorial, and the 2 factorials will cancel, which is equal to 1,814,400 if you multiply 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. Now, one of the difficulties in working with permutations is, first of all, you have to determine if you indeed have a permutation. Are you interested in the different number of arrangements or order? Is that important in the particular problem? So here we have an example where we do have a permutation. We have 6 different colored candles, so n is 6, and we want to take them and arrange them on the mantle 4 at a time. So yes, this is a permutation because every time we change the order we have a different arrangement. So this is equal to n factorial over n minus r factorial, which is equal to 6 factorial over 6 minus 4 factorial, which is equal to 6 factorial over 2 factorial. And this is one of the examples that we did earlier, which gives us 360 ways or different arrangements that I can take 6 different candles and choose 4 of those. Now, the next thing we're going to talk about is a combination. And a combination is different from a permutation. In a combination, we're interested in the grouping, not the order. So let's look at the same problem, but this time we're going to look at the number of combinations of the letters A, B, C taken 2 at a time. Remember, there are 6 permutations because every time I change the order, I have a different permutation of the letters A, B, C taken 2 at a time. But in a combination, we're not interested in the order. We're interested in the grouping itself. So how many combinations of the letters A, B, C are there taken two at a time? Well, there are only three. That's A, B, because A, B, and B, A are the same group. B, C, and again, you say, well, what about CB? Well, CB and BC would be two different permutations, but they're the same group. So that's only one combination and AC. Now, we also have a formula to determine the number of combinations of n objects taken r at a time. And that's equal to n factorial over r factorial times n minus r factorial. So the difference between the formulas for finding the number of combinations and permutations, you look up here, this is our formula for finding the number of permutations. So the difference is that in finding the number of combinations, there's an additional factor downstairs of r factorial. So in the previous example, we are taking or trying to find the number of combinations of three different objects taken two at a time. So n is 3 and r is 2. So that would be 3 factorial over 2 factorial times 3 minus 2 factorial, which would be equal to 3 factorial over 2 factorial times 1 factorial. And we already defined 1 factorial as 1, so this would simply be 3 times 2 factorial over 2 factorial. The 2 factorials would cancel and would give us 3, which is what we have obtained here. So again, let's find the number of combinations of 6 different objects taken 4 at a time. N is 6, R is 4, so we're going to use the formula n factorial over r factorial times n minus r factorial, which would be equal to 6 factorial, that's n, over r factorial, which is 4 factorial, times n minus r factorial would be 6 minus 4 factorial. So that would be 6 factorial over 4 factorial times 2 factorial. And again, I begin the factorialization of the largest number until I can find something that will cancel with a factorial downstairs. Now remember, you can only cancel equivalent factorials. So 6 factorial is equal to 6 times 5 times 4 factorial over 4 factorial times 2 factorial. So I can cancel the 4 factorials. So I have 6 times 5, and 2 factorial is 2 times 1, which is 2. So that's 30 over 2, which is 15. So I have 15 different combinations of 6 objects taken 4 at a time. Now, but I have 360 different permutations of 6 objects taken 4 at a time. So there's quite a difference here. Now, again, in these story problems, you've got to decide whether to use my formula for computing the number of combinations or the formula for computing the number of permutations. So let's look at a couple of examples here. How many different committees of 3 can be formed from a membership of 20? So if you got to ask yourself, is the order in which you choose the individuals important? And here it's not, because what we're talking about is committee. So if I choose Susie, Jim, and Sam to be my committee of 3, if I choose the same 3 in a different order, Sam, Jim, Susie, that would be a different permutation, but it's the same combination. It would be the same committee. So here I'm not interested in the different number of permutations or the order in which I choose. What I'm looking at here is the number of different groups that can be formed. That's what a committee is, a group from 20 members. Again, Susie, Jim, Sam, Susie, Susie, Jim, Sam, they're all the same committee, regardless of what order I choose them in. So the order is not important. So this is a combination of 20 different people taken 3 at a time. So my formula is n factorial over r factorial times n minus r factorial. N is 20, r is 3. So this is 20 factorial over r factorial, which is 3 factorial, times n minus r, which is 20 minus 3 factorial. So simplifying, this is 20 factorial over 3 factorial times 17 factorial. So I'm beginning the factorialization of the largest number until I get something that will cancel downstairs. So this is 20 times 19 times 18 times 17 factorial. So now I can cancel the 17 factorials. So I have 20 times 19 times 18, and I've got to simplify 3 factorial, so that's 3 times 2 times 1. So I'll multiply 20 times 19 times 18, and then I divide that by 3 times 2 times 1, which is 6. So that would give me upstairs 6,840 divided by 6, which would be equal to 1,140 different ways that I could select a committee of 3 from 20 members. Now the last problem that we'll look at is how many 5-card combinations can be dealt from 52 cards. So what I'm asking you is, how can we select 5 cards from 52? There are 52 cards in the standard deck. How many 5-card combinations would there be in a 52-card deck? So this is a combination. This is 52 factorial, which is n factorial, over r factorial, which is 5 factorial, times n minus r, which is 52 minus 5 factorial. This would be 52 factorial over 5 factorial times 47 factorial. And again, I begin the factorialization of the largest number until I get something which I can cancel downstairs. So that's 52 times 51 times 50 times 49 times 48 times 47 factorial. So now I can cancel the 47 factorials, and that still leaves me with 52 times 51 times 50 times 49 times 48, and what I need to do is expand 5 factorial. So that's 52 times 51 times 50 times 49 times 48 over 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is equal to, if you do the arithmetic here, upstairs I get 311,875,200 divided by 120, which gives me 2,598,960 possible combinations of 5 cards dealt from 52.